Mineral groups. So geologists divide the 3,000 or so minerals present on Earth into groups. Why? Because they're easier to study. We like to put a lot of things into groups to make them easier to find and study and look at and organize and whatnot. Each of these groups has a distinct chemical nature and specific characteristics. So the major groups we're going to talk about include the silicates, which we already talked about. Most of the minerals we have are silicates. You have carbonates, you have oxides, you have sulfides, you have sulfates, you have halides, and then we have the native elements. So our first major group is the silicates. And silicates are minerals that contain silicon and oxygen, and usually one or more additional elements. Okay, so these make up 96% of the minerals present in Earth's crust. So most of our minerals are silicates. Feldspar and quartz are silicates, and the two most common minerals. Okay, the basic building block is the silicon-oxygen tetrahedron. And then what is a tetrahedron? A tetrahedron is a geometric solid having four sides that are equilateral triangles resembling a pyramid, like the four-sided dice down here. There are equilateral triangles. There are four of them. You have 1, 2, 3, and then one on the bottom. So that is what a tetrahedron looks like. And what that looks like in terms of a silicate is we have a silicon atom in the middle, and then you have four oxygen atoms bound to that, and they arrange themselves basically like the points on one of these die. So bonding in silicon-oxygen tetrahedra. So silicon atoms have four valence electrons. Okay, so if we drew that out, we'd have a silicon atom, and then we'd have 1, 2, 3, 4 valence electrons, if we remember our Lewis structures. So they need four more. Okay, so they can bond with four oxygen atoms. So a silicon atom can easily bond with four oxygen atoms. So you'd have, say, an oxygen here that would share one atom there. And then actually, after you add all these oxygens here, you actually notice each one of them needs an extra electron. So really, your silicon-oxygen tetrahedron has a formula of SiO4 4 minus, because each oxygen atom also picks up an extra electron. Anyway, they can bond with four oxygen atoms, and then the oxygen atoms can be shared by tetrahedra, allowing a variety of combinations to form. So basically you have a silicon atom in the middle, you have four oxygen atoms, and then those oxygen atoms can be shared between different silicon atoms. Bonding between atoms determines several mineral properties, including cleavage and fracture. So as an example, mica is a sheet silicate. It has sheets of tetrahedra. These are your sheets of tetrahedra. And they are held together by potassium and aluminum ions. So here's potassium ions, here's some aluminum ions. So the sheets separate because those bonds are really weak. So these basically are negatively charged sheets of silicates. So these are basically sheets of silica-oxygen tetrahedra, and they are sort of loosely bound to other sheets by either potassium ions or aluminum ions. So that makes these have very weak planes right here. So you actually peel off sheets of this. So our main classes of silicates, we can have isolated tetrahedra, which would look something like this. You could have ring silicates, where you would have a series of these kind of formed in a ring. You could have single and double chain silicates. So we have a single chain here, we have double chain here. We have our sheet silicates. And then we have these other framework silicates, or these three-dimensional structure type silicates, like quartz is an example here. Okay, so we have different classes of silicates. So as an example, asbestos consists of double chains of tetrahedra that are weakly bonded together. This results in a mineral breaking into fibrous strands. So you got all these little strands that come off here. So it actually is very fibrous and woolly-like. This was used in construction materials and other products because it was heat resistant. It was also fibrous, so you can mix it in with other things, and it would actually add a lot of strength to materials because of the fibers. But the problem is this causes a lot of lung diseases like mesothelioma, asbestosis, lung cancer, etc. from inhaling asbestos, because it would get trapped in your lungs and you couldn't get it back out. So it would just sit there and cause different lung diseases. So it's been banned in a lot of uses, and actually costs a lot if you end up in a construction project where you have to remove asbestos. It actually costs quite a bit to actually do that properly. Mica. Mica is a sheet silicate. These are also called phyllosilicates. Phyll or fill means leaf. So these are like leaves or pages of a book. You can just peel off little thin sheets of this. So we talked about these being held together by the potassium and aluminum ions, which would bond to the negatively charged sheets of tetrahedra and would hold them together. But those sheets would easily separate because the attraction between the metal ions and the tetrahedra was really weak. So these could very easily be peeled off in very thin sheets. Thin enough, in fact, you could actually see through them. They used to use these to make windows for pilot lights on furnaces and stuff because they were heat resistant, but you could get a piece thin enough that you could see through it to see if the pilot light was lit. Then we have carbonates. So carbonates are minerals composed of one or more metallic elements and the carbonate ion, which is a CO3 2- ion. So we have some examples of calcite, which is calcium carbonate here. We have rhodochrosite, which is up here, which is a manganese carbonate. And then we have malachite, which is a copper 2 carbonate down here. Primary minerals in limestone and marble. So we'll talk more about that later, but marble comes from limestone initially. This is a metamorphic rock that comes from limestone, which is a sedimentary rock. But anyway, so these are the primary minerals in limestone and marble. Some of these have very distinctive colorations, such as colorful varieties of calcite. The malachite is this sort of blue-green. Rhodochrosite is a nice pink color. So carbonates. Oxides. So oxides are compounds of minerals with oxygen plus some metal. So some common iron oxides. We have hematite, which is actually our example here. Hema means blood, so it's sort of a reddish, rust-colored iron oxide. You have magnetite, which is also another iron oxide. These are two different iron oxides, two different iron ions here. Uraninite, which is a uranium oxide, is a good source of uranium. This was formerly called pitchblende. It looks something like this. This is actually what we use to get the uranium for nuclear power plants. You also have corundum, which is an aluminum oxide, which we mentioned in terms of Mohs scale. So Al2O3, which is corundum, which is an aluminum oxide. Some other groups, we have the sulfides, which are compounds with sulfur plus one or more other elements. So some examples, pyrite, which is a fool's gold, which is an iron sulfide, and cinnabar, which is a mercury sulfide. You have sulfates, which contain sulfate ions, which is sulfur with 4 oxygens. It's got a 2- charge. But you have a sulfate ion plus other elements. So anhydrite, which is calcium sulfate, which basically becomes gypsum board like drywall. Epsomite, which is magnesium sulfate. This actually forms Epsom salt. Halides contain chloride or fluoride plus a metal. So the halides are chloride, bromide, fluoride, etc., but contains these plus a metal. So halides, so sodium chloride, fluorite, calcium fluoride. Then you have native elements are made of a single element. So silver and gold are two good examples